Om Swastyastu, Assalamualaikum Warahmatullahi Wabarakatuh, Syallom, Namo Budaya, and hope to you all good, guys. And let me introduce myself. I'm Yudis Chrisantya, and my code is 23055310663. And our lecturer is Professor Dr. Tjokorda Gde Tirta Nindhia, MT M Eng. And in this Metallurgy with the code TM2301, I'm from Mechanical Engineering Technical Faculty, Udayana University. In this chapter, we will learn about heat treatment of steel. So the main reference of this material is from a book called Metallurgy for the Non-Metallurgists, the second edition, edited by Arthur C. Reardon. So in the heat treatment of steel, there have 10 of sub-chapter, and the first is the iron carbon system, common phase in steel, critical temperature and transformation diagrams, annealing and normalizing, type of annealing treatments, furnace, heating and induction, hardening and tempering, cold treating of steel, case hardening and heat treating equipment. Okay, we go to the first, the definition of heat treatment of steel. In the heat treatment of steel is defined as controlled heating and cooling of a solid metal or alloy by methods designed to change the microstructure obtain specific properties. Heat treating takes place below the solidus temperature of the alloy, and the purpose of the heating treatment is to change the microstructure and properties of the solid alloy. Almost all metal and alloys respond to some form of heat treatment in a broadest sense of the definition, but the response of the individual metals and alloy are by no means the same. And next we go to the first is the iron carbon system. Steel are in iron with a small amount of carbon alloy. Iron by itself has limited structural usefulness because it is soft. Like most pure metals, one way to increase the strength of pure metal is to add appropriate alloying element for solid solution strengthening. A more significant role of carbon is its effect on the formation of an iron paste called austenite. Iron is an allotropic element, which means that iron atoms change their crystal structure at some specific temperatures, known as transformation temperatures. Under normal conditions, austenite cannot exist at room temperature in a plain carbon steel, but only at elevated temperature within the austenite area, or we can say G, bounded by the lines AGFED. And the austenizing of steel is the first step in several different types of heating treatment, and the various kinds of transformation structure that occur when steel are cooled back down from the austenitic phase determine the resulting properties of steel. And carbon is almost insoluble in ferrite because the interstitial position available in the BCC lattice are not large enough to accommodate it. However, carbon is more soluble in austenite because the large interstices in FCC lattice are considerably more accommodating to carbon. So as you can see in here, carbon is more soluble in austenite, and here this is the austenite. This is the austenite because in the FCC lattice are considerably more accommodating to carbon. Next, we go to the common pairs in steel. Heating treatment of steel requires an understanding of both the equilibrium phase and the metastable phase that occur during heating and or cooling. For steel, the stable equilibrium phase includes ferrite, austenite, graphite, and to some extent cementite, as a very stable iron carbide. The metastable phase are perlite, martensite, and bainite. So in here we have three definition or three sub. That is from the first is cementite and perlite formation. The cementite of perlite formation, the equilibrium iron-carbon phase diagram applies when the temperature is held constant or when heating and cooling rates are slow enough to approximate equilibrium is isothermal condition. And here we can see eutectoid steel and perlite formation. The definition of eutectoid point on a phase diagram is the solid state version of eutectic melting point. Like eutectic transformation during solidification, a eutectoid point on a phase diagram is where a single solid phase transforms completely at one temperature into a mixture of two or more totally new solid phase. And the next one is hypotectoid steel. In here we can steel with less than 0.77% C are called hypotectoid steel. When low carbon steel with up to 0.30% Celsius or medium carbon steel with 0.30 to 0.60% Celsius are slowly cooled from the austenite phase. Some low carbon or ferrite forms first along austenite grain boundaries in the two phase in a Y plus A region of the phase diagrams. And the hypertectoid steels have carbon contents greater than the eutectoid composition of 0.77% Wt% Celsius. As the dissolved carbon increase in austenite, the iron atoms are pushed further apart. This structures the chemical bonds are there is a limit to how much strain energy the austenite can withstand. The next second one is the martensite. A martensite is a metastable structure that forms during rapid cooling to austenite, unlike the isothermal decomposition of phase constituents by diffusion. Martensite is not phase associated with thermal equilibrium. And the third the last is bainite. The bainite is distinct metastable phase and steel that occur when cooling rates are not rapid enough to produce martensite but are still fast enough so that carbon does not have enough time to diffuse from the perlite. And next we go to the third material is the critical temperature and transformation diagrams. In the critical temperatures of steel define either the onset or completion of a phase transformation. Three important critical temperatures in a steel heat treatment are: A1 is critical temperature for the start of the transformation to austenite, and the so-called eutectoid temperature, which is the into 100% austenite, is G. The ACM critical temperature is the high temperature boundary of the cementite in solid solution with austenite in hypertectoid steel, and the C over than 0.77% Celsius. So in table table 93, we can see this in here definition of critical transformation temperature in iron and steel. With the code ARCM in hypertectoid steel, the temperature when cementite begins to form precipitate during cooling of austenate carbon solid solution. Next, the transformation diagrams, the kinetic aspect of phase transformation, are as important as the equilibrium diagrams for the heat treatment of steel. Next, we go to the annealing and normalizing. In the annealing and the normalizing heat treatment are not limited to just hardening and tempering. Various annealing methods are useful in developing more uniform microstructure and other combination of properties such as ductility, formability, and machinability. General annealing thermal cycles. In annealing, we have annealing temperature may be classified as the first is subcritical annealing below the lower critical temperature A1, intercritical annealing above A1 but below the upper critical temperature A3 in the hypertectoid steel or ACM in hypertectoid steels. And the third is supercritical annealing to achieve full austenitization of either hypo or hypertectoid steel. And to get which may be used as guidelines for the development of successful and efficient annealing schedule, have a 7 rule. Is the all of the rule have a main recognition for make the success. And next we go to the type of annealing treatment. The types annealing treatment have various metallurgical purposes such as stress relief, precise sterilization, and sterilization. The figure also includes the temperature regions for the normalizing of steel, which is heat treatment to improve the uniformity of steel microstructure. In the type of annealing treatment, we have stress relief annealing. In the annealing at the subcritical temperature below AC1 includes there are different temperature regions. And the second is recrystallization annealing. When a cold worker metal are heated to a sufficiently high temperature, the badly deformation cold work grains are replaced by new strain-free grains. Spheroidizing. Depending on the time temperature exposure of a steel, the cementite carbide in a steel can form different morphologies. And a normalizing of steel. Steel is normalized to refine grain size, make its structure more uniform, make it more responsive to hardening, and improve machinability. And we go to the sixth part is the furnace heating and induction. Heat treatment of steel involves a wide variety of methods for annealing, normalizing, hardening, and tempering. Fuel-fired or electrically heated furnaces are used in a wide variety of configurations with various media. In the furnace heat-treating furnace can be generally classified as either batch or continuous furnace. In a batch-type furnace, where loads are placed in the furnace and its load are brought up to temperature together. And depending on the process, the furnace may or may not be cooled before it is opened and load removed. Continuous type furnace, which operation in a uninterrupted cycle as workpiece pass over a stationary head or the heart itself moves. Both furnace, or we can see in here, are basic type of Batch furnace more complex configuration allow for horizontal loading. Fig is in here the horizontal loading or vertical loading. This is the vertical loading or the workpiece into a furnace. And induction heating is a method of heating electrically conductive material by the application of the varying magnetic field whose line of force enter the workpiece. And other advantage of induction heating treating, which stem from this non-contact method and its generation of heat within the workpiece, are ease of automation and control, reduced floor space requirement, quiet and clean work condition, suitability for integration in a production line or general work area due to the elimination of secondary or radiate heating. And the 5 is self-monitoring capability. Next, we go to the hardening and tempering. In the hardening of steel involves a 3-step process of austenitization, quenching, and tempering. Sometimes an additional step of cold treating is done at low temperature below the martensite finish temperature of the steel. In the quenching refers to the process of rapidly cooling metal parts from the austenitizing or solution treating temperature, typically from within the range of 815 to 870 degrees Celsius, which is 1050 to 1500 to 1600 degrees Fahrenheit for hardening medium and low carbon steel to temperature as high as 1232 degrees Celsius, which is 2250 degrees Fahrenheit for hardening specific grades of high-speed steel. In the quench media, successful hardening usually means achieving the required microstructure hardened strength or toughness while minimizing residual stress. Tempering hardened steel can be tempered to reduce hardness and to increase toughness. And next, we go to the cold treating and steel. After hardening, some alloys retain a significant amount of austenite that does not transforms to martensite. A good example of such a grade is D2 tool steel. It is not unusual for D2 to have as much as 20% retained austenite after undergoing standard heat treatment. And here we can get the equipment for a cold treating. A simple hole type deep freezing can be used for transformation of austenite to martensite. Temperature will be approximately in the minus 18 degrees Celsius or 0 degrees Fahrenheit. In some instances, hardness tests can be used to determine if this type of cold treating will be helpful. And the next is the case hardening. Case hardening is the generic term used for several processes that put a hardware-resistant surface layer on part. There are two distinctly different approaches to the various methods for surface hardening. The first is overlay and coating method that involves an intentional build-up or addition of new layer. And the second is surface treatment, that involves surface and subsurface modification without any intentional build-up or increase in part dimension. In here we can get two sub. The first is diffusion methods of case hardening. Surface hardening by diffusion involves the chemical modification of the surface. The basic process uses thermochemical because some heat is needed to enhance the diffusion of hardening species into the surface and subsurface region of part. And the localized hardening process, one way to produce a part with a hard surface and relatively soft core without altering composition is to use a steel with low hardenability. It's like one that does not have drought hardening capability. Other technical include seal hardening, flame hardening, and induction hardening. And the last part is heat treating equipment. In simple terms, industrial heat treating furnaces are insulated enclosures designed to deliver heat to workloads for thermal processing. Basic elements of construction include an outer shell, refractory walls, hard roof, a source of heat electric or combustible fuel, and means of offsetting a workload, moving it through the furnace if necessary and removing it. And we go to the first is the batch furnace, are loaded with a charge then closed for a established heating cycle. And the continuous furnace are basically of the in one and out the other type and are ordinarily used for continuous volume production. So in here there are four chapter. The first is can furnace Ltd, and this is a card of surface combustion, and in here we can see a Seco or which, and then have more again. And next is the furnace atmosphere, and many heat treating operations part must be heated under conditions that prevent scaling and or loss of carbon. As still in the heated, the surface become more active chemical. Next is the vacuum furnace. Heated chamber in this type of furnace are activated to a very low level depending on the materials and process by which metal is being treated. And in a plasma furnace, a glow discharge plasma occurs when a direct current DC of a few hundred volt is applied to two metal electrodes in an enclosure evacuated to a few hundred pascals is a PA of a pressure. And the next is the fluidized bed furnace. Consists of a bed of mobile insert particles, usually aluminum oxide, suspended by the combustion of fuel-air mixture, flowing upward through the bed. And last is the salt and liquid bed pot furnace. In the bed of molten salt or metal can be used for both heat treating and heating application. Pot furnaces are unique in that the media being melt is the source of heat for this operation. Heating in a molten metal, usually lead, is an age-old practice. And that's all our my presentation. Thank you for watching my presentation. I apologize if there is something problem or missing in my presentation. And the last, I will close with Om Santi 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 Om. Assalamualaikum warahmatullahi wabarakatuh. Syallom, Namo Budaya, and bye bye.